Kia ora koutou, good afternoon and welcome to our fifth session in the updates for the Natural Environment Recovery Program. I'm Chrissy Williams, Program Leader for the program. So today we have three amazing speakers who could probably each talk for a couple of hours, so keeping them to time to allow some questions and discussion at the end is going to be a challenge for all of us, so I'll try and do that. Today we're talking about the coasts and estuaries. We have three speakers from the University of Canterbury. We have Deirdre Hart and Matthew Hughes, and from NIWA we have Richard Measures, and I'm sure they can mention a little bit about other work they're doing if they feel that appropriate. I won't spend time introducing them further than that. Again, just a reminder where all this fits in the bigger picture. So under the recovery strategy, as you've seen before, there's the natural environment goals, and today we're talking about estuaries and coasts. So it fits under the goal of improving the quality and functions of estuaries, but also importantly understanding what's happening in the coast and anticipating what might happen in the future. For the Natural Environment Recovery Program, the NERP, there's a number of projects, 17 of them, and the second project is investigating and monitoring coasts and estuaries, and that's what the focus is today. So those three speakers will take the next 40 minutes or so, and as I said, then we'll have questions and discussion.
Thank you, Chrissy, and tēnā koutou. As Chrissy said, I come from the University of Canterbury and I'm a coastal scientist, and we've got a geospatial specialist, Matthew Hughes, with us today, and a hydrological modeller in Richard Measures. Our title was Earthquake Effects on Coasts and the Estuaries, but it's a little bit misleading. We are going to talk about earthquake effects on the coasts and the estuaries, but to many people the coasts and the estuaries are the present edge of the ocean. And that's quite a narrow area in a lot of people's minds. To me as a coastal scientist, coastal and river environments today and the past are what have shaped the landform that our city sits on. So it extends a lot further inland than you might imagine, and so does our talk. So I'll talk about the coastal and river quakes concept, which is a research project concept that we're working on with a number of other people from Canterbury and other organisations. Then Matthew's going to talk about the earthquake sequence and the changes in the terrestrial environment, so the deformation of the land from that sequence. Richard will talk about specifics of change in the Avon Heathcote estuary, Ihutai, and the river channels as well will be mentioned by Matthew. Then we'll have a bit of a synthesis and a future vision, and hopefully we'll end on a bit of a positive note, or I'm going to try and sell it as a positive note. I've got a photo here borrowed from ECAN and some storms that we had on a nice big high tide back in 2001, but I've put a question mark there. Is this the sort of future that we're looking at in our now lowered city with sea level rise into the future? So the coastal and river quakes concept. When the earthquakes first occurred, there was an abundance of talks about seismicity, about aftershocks. But to me, as a geomorphologist and an ecologist, that didn't necessarily explain the damage patterns that we see on the surface. And I talked a lot with the lifelines engineers, the people that look at the horizontal infrastructure and the damage to that system across our city, and the patterns that they saw weren't necessarily corresponding just to seismic factors. So we came up with a hypothesis that when you have a seismic event and it occurs in a coastal plain environment, so you've got a coasts present and past, you've got rivers draining a very flat landform, then a lot of the damage patterns after an earthquake are going to be explained by interactions between those coastal and river environments and the seismicity. So you can't use earthquake data alone, you need to involve the whole of the environment to understand the damage patterns. Then we thought about it a little bit further and started to notice some of the changes that the earthquakes have brought to our city, and came up with the idea that there was a cascade of effects in these coastal and river environments, changes in all the other hazards that we might not have thought of as earthquake hazards beforehand. Things like flooding, for example, coming from rainfall, hydrological flooding, draining across our city. A lot of people don't necessarily associate flooding as an earthquake or an earthquake-enhanced hazard, but we started to see the links or the cascade. In hindsight, it was a bit of a no-brainer because these kind of linkages have happened in many different places across our globe in the past, recently and quite far back into the past. Another nice example of what's happened to Christchurch happened in Charleston in North Carolina in the end of the 1800s, and they had liquefaction like what we've had. They had a lot of very similar effects. They had a different built environment, a different lifelines kind of situation because it was the 1800s, but a lot of the physical changes that you see in the environment were similar. And we came up with the idea that this was related to the idea that we're on a coastal plain. So we're on a very low-lying, low elevation, relatively flat plain next to the coast, and it's a very recent plain. It's only Holocene that these sediments have been laid down on the surface. Underneath, we've got 600 metres or so of gravel and sand lenses, interactions between rivers and coasts, but the surface layer is a very recent, predominantly coastal formation. So that's the coastal and river quakes idea in a nutshell. Just to illustrate that a little bit, here we've got the city, just to situate you, the Avon Heathcote Estuary, New Brighton Spit. This dotted line here represents the shoreline approximately 6,500 years ago. So Riccarton was coastal real estate 6,500 years ago. And everything east of the university, it's good when we come up with an idea that sort of situates us in the centre of things when we're studying. Everything east of Riccarton and the university sort of area is very, very recent. Now, the correlation between this line and other kinds of damage pattern and hazards lines is quite disquieting. So if you're looking for parts of the city that were badly damaged, you go east of this line. And now we're looking, we've got a renewed focus on groundwater levels and on what elevated groundwater levels over the next 100 years will mean for the transition of the liquefaction risk area inland, and we come up with this line again. So this line represents recent sediments everywhere east. It represents very low elevation land. It represents a very high water table. Some of the ingredients you need to get damage in an earthquake sequence. This is underneath the law courts in the 1970s, photograph supplied by Bob Kirk. And if we look in at one of these profiles down through the ground under the law courts, it looks like I've taken the photo of the inside of a dune. So you can see those recent coastal sediments on the surface. But it's not just the natural environment. I'm a geographer as well as a coastal scientist, and we like to look at the human environment and how that interacts with our natural environment. Now, our built environment is very much focused on our blue edges as well. We like to live by coastlines. We like to have stream boundaries on our real estate. So naturally, we have put a lot of our infrastructure and a lot of our assets and a lot of our people very close to blue edge environments or coasts and rivers. And there's a photograph by Marnie Brosnan from Sumner just showing the effect of that. Again, thinking lifelines, the horizontal infrastructure that allows our city to function underneath the ground, underneath the roads. When you are in a coastal and river-dominated coastal plain, you have a complicated shoreline that you have to fit your city around, and you have a heavy reliance on bridges because you've got to get across waterways and make connections for our lifeline systems. But these are really weak points when it comes to earthquakes. So we've got a reliance on these weak points. And we also don't have the extra redundancy that we have when you have a grid system across your entire city. So anyone who's living out east at the moment will realise the disruption when you get the lifeline systems broken and repaired. If you just can't go another block down to get around all the roadworks, it's a lot less sustainable environment to build in.
Just quickly, I'm an earth and environmental scientist and a geospatial analyst. That means I make maps of things. I have a background in climate change research, and how climate changes over the last few million years have shaped the landscapes that we live on now. I'm going to give a very brief overview of the physical effects of the earthquakes on the landscape in Christchurch. I refer to it as urban landscape evolution. So the landscape has evolved, its geomorphology, the shape of the earth has changed through the earthquakes. What we see here is essentially the regional context. Here is the current location of the Waimakariri River. What these patches here are its former channels. So that we know through geological evidence that the Waimak used to come south of the peninsula, and over the last 1,000 years has migrated north, has at a few periods over the last several centuries issued through where the current estuary is now, and it is now sort of settled in this location. It's a very dynamic landform. Here's the urban boundary for Christchurch City, and what these red lines here are known previously mapped faults in the hard rock underlying the Western Plains and also into the foothills of the Southern Alps here. We knew that Christchurch was going to get smacked by an earthquake one day. Most of our previous focus was on the Alpine Fault. A lot of our modelling and understanding and predictions of what would happen in Christchurch, some of which came to pass, were based upon the idea that it was going to be the Alpine Fault with a very large magnitude quake with high levels of shaking over many minutes would impact Christchurch. The other thing we were worried about was the Hope Fault, which cuts through Kaikoura and offshore Kaikoura. Both of those things could also go at any moment or any day as well. I guess before 4th of September 2010, I never imagined that we would actually get earthquakes impacting Christchurch generated so locally. And so this is what happened on the 4th of September 2010. That little star there is the epicentre of the 7.1 magnitude quake that kicked off early that morning. You see that little pink rectangle there with a slightly thickened edge up the top? We've actually mapped the causative faults, we call them. We've mapped the faults, we know exactly where they are that gave rise to these things. So over several seconds, this thing unzipped and ripped here. And so that's the top edge there, so it's sort of dipping down into the ground there. That kicked off, and then there's a whole series of other faults ruptured over the next couple of minutes. And this was expressed at the surface, and we call it the Greendale Fault surface trace through here. And we've all seen those photos of this massive rip across the farmland. So that's what that is. And we thought we'd had our big one. Once in a generation, once in a multiple generation event. I remember thinking to myself, thank goodness that didn't happen at lunchtime, because look at the unreinforced masonry buildings that collapsed and their facades that went into the streets early that morning. Little did we know that what that event did is displace stresses throughout the fractured rock that underlies the plains, fractured like a broken china plate. And what we see here are the faults that fault planes that kicked off on 22nd of February 2011, 13th of June 2011, and 23rd of December 2011. So a couple of things to note here is that the initial event set off these aftershocks, major aftershocks. Literally, what does that mean? It means that stress and pressure is released in that first event. That stress is not completely dissipated through the shaking and dissipation of those energies as rumbling and noise and those sorts of things. A lot of that stress is displaced to other faults. And we now know there's been an eastward migration of this cluster of faults. And that's what we now call the Canterbury earthquake sequence. And we now know with high precision the actual faults that failed and slipped to produce those earthquakes. This had distinct geomorphological effects on Christchurch. very quickly, LiDAR data was flown. You've probably heard of LiDAR data spoken about in the media and things like that. What that is that you get a piece of equipment that's put onto the bottom of an aircraft. It's flown across the landscape and it fires a laser at the ground. It's a very high precision global positioning system in the plane, so it knows exactly how high it is above the ground, fires a laser at the ground, and the signal bounces back to the airplane. And the time of that firing and return gives you a map of the ground surface, essentially. So if you take two of these maps and subtract one from the other, you get a difference. You can actually start to see changes in elevation. And this is what we see comparing the 2003 data that were flown by the Regional Council for modelling purposes, flood modelling purposes. And this was flown the day after the September quake. Just very quickly, we can see a lot of the map is the sort of lemony, sort of honey-coloured yellow colour. Basically what that means is that the data is telling us that across much of this area, the ground has basically moved between 10 to 20 centimetres up and down. That's actually within the error of the technique. It's very difficult to say anything actually happened if the ground actually did go up about 10 or 20 centimetres. The data isn't really giving us any conclusive evidence of that particular movement. But interestingly, we do see a bunch of other stuff happening. For example, see this blue stuff along the coast? That's the build-up of sediment and sand between 2003 and late 2010. And also here, for example, what we're seeing is infilling or for urban and industrial development. See these pinks and reds all dotted around the place? You can see them around the place here. Those are excavations, pits being opened up, things being quarried, open ground for development. They're just captured with this technique. This is what it looks like after the 22nd of February earthquake. We're starting to see a lot of signal coming through the noise here. Two things I want you to notice is that in this part of Christchurch here, that what this means is uplift. So here's one of the major faults that actually kicked off on the 22nd of February. And what we're seeing here is the ground has been pushed up tectonically. So a block of the earth has been punched up and much of the rest of the city dropped down tectonically a maximum of about 20 centimetres. We actually had a much greater subsidence across the city than 20 centimetres, however, and that is due to liquefaction and lateral spreading. And so the shaking produced the liquefaction process. I don't have time to go into the details of exactly how that works here, but the practical effect is that water is expelled from the ground and it takes with it sediment. And the ground is going to drop by how much of that stuff is pumped out to the top of the ground. Now this data was flown several weeks after the event. That enabled the Farming Army and the Student Army and the Council to scrape away all the sediment liquefaction, the liquefaction sediment off the ground. So we actually got a realistic picture of what the ground had done. June and 23rd December. So what we're seeing here is, from a map perspective here, we're seeing quite a large expansion in space this is minus 0.4 metres, so that's 40 centimetres to a metre drop across the city. So Christchurch has experienced significant and spatially extensive subsidence due to the earthquakes, due to both tectonic subsidence and settling of the ground through, due to liquefaction and lateral spreading. This is a slice through the Avon River. This light grey line is the ground surface and the river profile in 2008, and this darker line here is after it was taken after the June 13 quake. So essentially what this is saying is that the bed of the river has gone up because due to sedimentation, the liquefaction sediment is into the river. The banks have narrowed due to lateral spreading, so the bank has literally slid into the river itself. And fundamentally, of crucial importance, is that the floodplains on either side of the river itself have dropped due to liquefaction. And so the capacity of the river to contain and transmit water has decreased, and at the same time, the floodplains have dropped, enhancing the flood risk.
Okay, so after the earthquakes, well, before the earthquakes, NERP were already doing some work on the Avon Heathcote estuary, looking at the changes going on in the estuary as a result of the wastewater diversion. So we were already working there, and ECAN approached us to say, we really want you to look at what the effects of the earthquake are on the estuary. So what we're looking at here, on the left-hand side, is just a map of the estuary bed. So that's put together from a number of different sources of information. So that some of that is from the LiDAR that Matthew talked about. That only covers the dry areas, so that was flown at low tide, and that gives us all the mud flats and the sandbanks. That's all covered by the LiDAR, and then the deeper channels and things, that was filled in through conventional survey techniques. So that's echo sounders mounted on a boat. We drive around, measure the bed of the estuary. So that map on the left is a map post-earthquake, and then we went back and we collected up all the different data we could pre-earthquake, and we made a similar map. And what you can see there on the right is just, as Matthew showed with the LiDAR, that's the same, but for the bed of the estuary. So that the green colours are where the bed of the estuary has been uplifted, and the red areas are where the bed of the estuary has dropped. And I guess the main story there from that picture is that the majority of the bed of the estuary has risen by up to about 0.4, 0.5 of a metre. And the north end of the estuary, where the Avon comes in, that's dropped by a similar amount. So the next question is really, so what does that mean for the estuary? So to answer that question, we built a hydraulic model of the estuary. So this is it's a computer model. It's got divides the estuary up into lots of small cells, about 10 to 20 metre cells, and then it simulates the flow of water in and out of the estuary over the tides with the rivers flowing through. And we built two models, one for the pre-earthquake estuary and one for the post-earthquake. This was supposed to be an animation, but it's not working. But I guess the message was, what we're looking at there is the water depth at low tide in those two pictures, really. But it's quite difficult to see, just looking at the results, what the changes mean. So I guess the next few slides, I'm just going to take you through what that model showed the earthquake did to the flows and the water and the salinity within the estuary. So I guess one of the important things in an estuary is that at high tide, most of it's underwater. At low tide, large areas of mudflat are exposed. And that's quite important for things like the seabirds which feed on the flats, the various different species of plants which grow around the estuary margins. What this map here is showing is the proportion of time that the bed of the estuary is above the water surface. So on the left, we've got the pre-earthquake condition, on the right, post-earthquake, and I'm going to be showing you a few maps like this with different things. But the blue colours are wet for longer, so they're wet most of the time. The browny colours are kind of dry most of the time, and we can see sort of because of that uplift, the southern half of the estuary, so that's kind of McCormick's Bay, Humphreys Basin on the west side, that's got a lot drier, so the bed's exposed a lot longer, and that has big impacts for the different species of plants and animals that live there. And that the northern part of the estuary has got a lot wetter. Now, the other change, as well as the exposure of the bed surface above the water level, is the volume of water moving in and out of the estuary on each tide. That's the tidal prism. So if we look at the estuary as a whole, and we take the flow of water through the mouth, so we're looking at the volume of water that moves in and out on each tide. That's reduced as a result of the earthquake. So that's reduced by about 15%. And that flow of water in and out is what maintains those channels. It maintains the size of the estuary mouth. The sea is constantly, the waves are constantly piling sediment from the beaches into the mouth of the estuary, and it's that flow of water through it that maintains the channel and the mouth of the estuary. So we'd expect to see that channel get smaller. Again, looking at that tidal prism, the biggest change in the estuary really is McCormick's Basin. And the volume of water in McCormick's Bay has got 50% smaller. There's half as much water going in and out on every tide. So that's probably the biggest magnitude change, looking at the estuary as a whole, is occurring in that area. So So this is shear stress, which I guess is the force of the water on the bed of the estuary. So as the tide moves in and out, the water rushing over the surface is applying a force onto the surface, and it's that force which is moving sediment, it's maintaining those channels. And just looking at the differences here, what we can see is at the mouth of the estuary, in this sort of main channel, the shear stress has dropped because there's less flow of water going in and out. So what we'd expect is that channel's going to get smaller, sediment's going to settle out there, and this whole channel is going to reduce in size. Interesting, in other areas of the estuary, for example in this channel leading to the Heathcote River, the shear stress has increased, and that's because the bed's come up and the channel's actually got a lot smaller. And what we're saying is it's going to try and re-erode back to a sort of similar-ish size to it was before the earthquake. And similarly in the north of the estuary, the shear stress has dropped, and we'd expect to see a bit of deposition in that area. Just moving on into the rivers, so the computer model, as well as looking at the flow of water, the velocity and the depth, it also simulates the salinity. And what this graph is showing is this is just the Heathcote River at the top, the Avon River at the bottom, and this is the distance upstream of the main bridges. So this is moving up the river, up the Heathcote River above the Ferry Road Bridge, and moving up the Avon River above the Bridge Street Bridge. And the two pairs of lines, the top line is the maximum salinity. So at high tide, when the salt wedge is pushed as far up the river it's going to get, this is what the salinity is. So we could say at high tide, on a high spring tide, the maximum salinity at 4 kilometres upstream of Ferrymead Bridge before the earthquake was the blue line, and after the earthquake is the red line. So because the Heathcote River's gone up, the salt wedge isn't actually pushing as far up the river as it did before. So the river's got fresher, effectively, and that difference is quite significant. We're talking about a kilometre, the model's suggesting. So the salt wedge is pushing a kilometre less up the river than it was before, and that's affecting things like the riparian vegetation, the location of whitebait spawning sites. It affects quite a lot of the ecology. On the Avon River, the changes are a lot smaller. Sorry, the bottom two lines are the mean salinity over time, so that's kind of an average of the low and high tide. And it shows a similar thing. The Avon River, the changes are a lot smaller, and I guess although the river's subsided, lateral spreading and things have reduced the size of the channel as well, and the effects sort of cancel each other out, so that the major change in salinity was actually on the Heathcote River. And I think this is my last slide. So this is just looking again at the mouth of the estuary. So the graph here is showing a cross-section through the mouth of the estuary from the Brighton Spit through to Shag Rock. And the blue line through here is what the mouth looked like in 1998. So this was the last survey we had pre-earthquake. Nobody had surveyed it for a while. So there's obviously a period of natural change, but also a big effect of the earthquake. So looking immediately after the earthquake, this is the area of that cross-section, and we can see the red line was immediately after the earthquake, and we would expect to see it get smaller because, as I've said, the tidal prism reduced, the volume of water going in and out reduced, and the shear stress through that channel reduced. We'd expect to see some sedimentation. And if we skip forwards to January 2013, there had been a lot, and we said, oh yeah, that's what we expect, great, it's got a lot smaller. Then we did another survey the end of last year, September, and we found it's actually back almost as big as it was immediately post-earthquake. So I guess it's raising a lot of questions. Is that just the natural dynamics of the mouth? It's getting bigger and smaller all the time, and those changes are bigger than any earthquake effect, or has the earthquake indeed had an effect, and those changes are a response to it? So I guess this is kind of ongoing work, and I'm not really answering any questions here, but it's just showing the scale of those changes occurring following on from the earthquake. It's not just the changes that happened immediately at the time, because sort of some of these processes take a while, they're influencing erosion and deposition. It takes a while, and we're still seeing changes today.
We need to talk about sea level. The flooding I mentioned before, the increased flooding hazard due to subsidence, It's mainly that flooding hazard is mainly due to weather events, overland flow and runoff of rainwaters into the rivers and spilling over the rivers onto the floodplains, causing the increased flooding issues we have in Christchurch now. But of course, if the ground is dropped relative to where high tide is each day, then you have what we call a relative sea level rise. But we've also had relative sea level fall. And here's an example of that here. So here's one of our LiDAR differencing maps showing the vertical changes. You can see the uplift area here in the southern part. Much of the rest of this area has dropped. And that purple star there is just taken on the edge of the Bromley sewage treatment ponds there. So this is this photo here. And this beach has gone up. And so what this means is that at high tide is not penetrating inland as far as it used to. And what we're seeing here, you see these little plants here? I'm not a botanist, sorry. I had a botanist friend take me out and show me around. But these plants are not tolerant of salty conditions. And they're starting to migrate out across the beach, and they're recolonizing this beach. So that means that their feet, their roots, are not getting wet with salty water as much as they used to. Certainly not to the point where it inhibits their growth and colonization of this area. This is really interesting because even in the absence of this amazing LiDAR data set, this basically the height of our current technological capability to quantitatively measure ground surface changes. If we didn't have that, actually the plants are telling us what happened. And these plants are telling us that this part of Christchurch has gone up. We're now across the other side of the estuary here, where it's gone down, where the land has gone down. And so we're at the margins here. The margins between basically the estuarine or marine and terrestrial interface. And prior to the earthquakes all around here, despite all the development that's gone on around the place, all the landscaping, and building of roads and bridges and things like that, there were significant areas of this marshland populated by marshland plants, habituated or adapted through evolution by natural selection to this environment. We sometimes have referred to this ecosystem as the botanic gardens of the estuary. It's now dying off because it's dropped. The high tides are now penetrating further into this environment, and so these plants are dying off due to salt toxicity. There's also something else going on. Prior to the quakes, there was actually groundwater coming up from beneath and sort of diluting the saltiness of this area as well. Natural springs, sort of making the water not quite so brackish or salty. Now with liquefaction and settlement and disruption of the sediments through that process as well, that intrusion or the introduction of fresher water helping to maintain these ecosystems has been shut off. So this double effect of the drop leading to increased tidal saltwater intrusion, combined with the shutting off of the freshwater groundwater sustaining this ecosystem, means that this ecosystem is dying off. And again, we didn't need the LiDAR data to tell us this. The plants are telling us exactly what happened. This has a whole range of different implications. For a start, these plants are binding the sediment. And so their die-off, it's going to be interesting to see how this part of the coastline around the estuary responds to storm events, for example, and extreme tides, the surging of the waters in these dynamic situations. With these plants gone, are we going to see increased sediment movement and erosion due to the relative sea level rise? Another thing I want to raise, just before Deirdre finishes off, is we've had sea level rise in Christchurch because the land's dropped. Now that sea level rise is probably up to a metre or more in some places, is equivalent to decades or centuries of climatic sea level rise due to anthropogenic global warming, which we haven't raised yet, and I'm not going to perhaps talk about any further unless we have some questions afterwards. But what we're seeing here is a model, an example of how coastlines will react to sea level rise in future due to climatic changes. But it's the seismic earthquake impacts that are actually telling us this lesson. This isn't unique to Christchurch. There are coastal communities all around the world, huge megacities through to small fishing villages that naturally subside anyway. Having earthquakes underneath your city can accelerate that process, and this combined with climatic sea level rise due to climate change poses significant issues that as a coastal community we need to think seriously about. And with that, I'll pass over to Deirdre to finish up.
Okay, so Matthew's taken us to a nice point there, bringing us to look at hazards and to pay attention to hazards. I started off by saying that immediately after the earthquakes, I went to a lot of talks about seismicity and about how earthquakes create land damage, is what the engineers call it, or geomorphic change to me as a coastal scientist. And these are the kind of models that you can look at. So here we've got seismic energy being released from faulting that creates strong ground motion. When it hits topographic relief, in other words steeper slopes, then some of it might fall over and you get landslides, and topographic relief also amplifies ground shaking. So because you've got these sharp edges, you get the waves moving through the ground and interacting on the corners and accelerating things like landslides. When the ground motion goes through soil deposits, you get liquefaction, amplified ground shaking again, and tsunamis off to the side. So there's a lot of seismic features in there. But I think in order to understand what causes these changes, you need to look at the pre-existing coastal and river environments. So we are on a very recent coastal plain, a Holocene progradational plain that is flat. It has readily liquefiable sediments. Because it's flat and close to sea level, it has a high water table, which is the third ingredient you need for liquefaction, in addition to the sediments and the ground shaking. So a lot of the precursor conditions for the changes that we're seeing as a result of the earthquakes are due to our natural environment, the fact that we've built on this flat swampy plain and half drained it. The steep edges as well, you've got riverbanks, you've got coastal cliffs, so our topographic relief is very much linked to the past coastal and river environment as well as the present. What about the flow-on effects, where you get subsidence and the rafting or the movement of the surface crust because of the liquefied layer underneath? This is again something that occurs in a coastal and river proximal environment. So the shaking is only one small part of understanding earthquake effects. You need to look at the river and the coast environments. Same with our lifeline systems, our bridges, our roads around these complicated shorelines and across rivers. That's coastal and river features determining the change and the damage. And then we've got the cascade concept that I touched on at the start of the talk, the flow-on effects on other hazards. So we've got an altered risk of river flooding, coastal flooding in the estuary with the subsided area in the north. Interestingly, the north of the estuary was always the flood-prone area, and that's sunk more. We've got relative sea level rise. So relative sea level rise is not the water level going up and down, theoretically. It's the water level in comparison to where the land is. So as far as our perspective as terrestrial people living on the land, where is the sea level in comparison to where we are? Because we've sunk, that looks like sea level rise. We've got relative sea level rise. Tsunami hazard has changed because the vulnerable points to tsunami hazard are the low points around our coastal edge and up our river channels. And those low points have become lower in a lot of cases. Shoreline erosion, what's happened to our sediment deposits? All of the sediment released by the earthquakes, you'd think that would be a good thing for shorelines, but some of it's quite fine. Maybe it's starting to clog up the geomorphic systems, and that's not so good. So pluses and minuses for that hazard. Waterway pollution. massive amounts of release of sediments with everything that's stuck to those sediments, as well as breakage in the wastewater lifeline system, interacting with our stormwater system, interacting with our waterways, all of these cascading hazard effects from the earthquake sequence. When you look at the likelihood or the return period of these different kinds of hazards, our earthquake sequence has quite a low return period. It only occurs, statistically speaking, every now and again. Some of these other hazards are a lot more certain. Sea level rise, for example. If we take away the anthropogenic, the human component, and we just look at background sea level rise over the last interglacial that we're in, this warm period, we've had sea level rise of about 20 centimetres over the last 100 years. And that's just the background sea level rise rate without adding on anthropogenic enhancement of that sea level rise through climate change. So some of these cascading effects are to hazards that we were already facing and that are much more likely to affect us within our lifetime. Richard mentioned that, or I think Matthew mentioned that some of the LIDAR was flown before the earthquakes to study flooding, and that some of the estuary studies were to study changes in the estuary and its effect on drainage of our city. So before the earthquakes, flooding was a really big hazard here. Then we had the earthquakes, we had a lot of disruption, and we're back to a situation where we need to pay attention to all of these cascading hazards. Another thing that we learnt from the effects of the earthquakes on coasts and rivers is that when you have any major hazard event, you need to go back to the drawing board with all the other kinds of hazards that affect your area and to re-examine the risk. So this is a multi-hazards perspective. Traditionally, under just a individual hazards lens, we would look at hazards like earthquake risk, sea storms. Sea storms seem like a totally different thing to earthquakes. And urban flooding seems like something quite different to earthquakes. So we would study the natural environment and the built environment layers where the people and the infrastructure and the resources are, and we would stack up all that information to get an idea of earthquake risk. And we'd do the same for sea storms and for urban flooding. And because they're all co-located within our urban environment, we would build up this picture of hazard risk. But I think this is far too simplistic a model with the hindsight of the earthquake sequence. What we've got to do is this. We've got to look within each layer at changes in the natural environment, the built environment, in the population, in where people are living and how they're coping, and study all of the interrelations between these different hazards. And this is a multi-hazards perspective. Everything's connected. And so we study the risks in series, not in parallel. We've got a big team looking at a whole lot of multi-hazards after the earthquakes, and we're just using Christchurch as an example. Others are looking at Tohoku and doing comparisons with Japan and what's happened in Christchurch. And one of my master's students, David Holland, who's also working with Sonia Giovinazzi in engineering. So you've got multidisciplinary teams, just like us today, working across the boundaries. He's looking at the enhancement of the flood risk after the earthquakes, and he's focusing mainly on the stormwater system. So this is a model that Dave's come up with of the different components of a stormwater system. And you can see we have built components like pipes through the ground. We have natural components like swales and drainage basins in a natural environment, and we have river channels which have natural and built components to them. Stop banks, river channels that were here before humans but which have been changed by us. And he's picking apart each of these little components and looking at the earthquake changes to understand how our flood risk has changed. Now I said I was going to try and end on a positive note. And that's the idea of our city as a sea level rise or sea level change laboratory. So just to drill home that relative sea level idea, a simple model here. We've got sea level out here, we've got our land level, and underneath we've got the fresh water table. Now the groundwater table underneath our land slopes down to sea level. So if sea level changes, the slope of that groundwater table will also change. Same with our rivers. So our rivers slope down to meet the sea. And if the level of the sea changes relative to where the rivers are, there's going to be adjustments in those river channels to correct that slope and to take it gently down to the sea. So we've had this relative change in the land level compared to the sea level. This sea level is higher compared to where we are residing now today. We've had land subsidence, so relative sea level rise. And sea level rise, as I said, has been happening over the last century. We had 20 centimetres or more, and we're forecast to have a lot more than that over the next century. It's a very difficult hazard to respond to in a planning sense, in a socio-economic sense, because it's really gradual. It just creeps up on us. We notice it when we have events like storms, big storm inundations on high tides, when we have events like the rainfall that we had in March last year, big rainfall events. And that was quite a painful rainfall event for a lot of people who suffered flooding across the city. But I'd like to try and think of it over the longer term as quite a positive thing. What if we'd done all of our earthquake repairs to our coastal and river environments, and in 20 years' time we discovered that we had an enhanced flood risk? Much better to find out now. Also, as humans, it's a lot easier to adapt to an instantaneous new reality. So we've had up to 1 metre of sea level rise almost instantaneously, just within a few years, over the course of a few events. So we don't have to plan for the next 100 years at the moment, we just have to deal with what we've got straight away. And because it's so pronounced, we can't avoid it. We can't imagine that it's not going to happen, that it's not there. So we're a lot further along in the acceptance stage of dealing with this hazard and in recovering our natural environment. So I think that over the long term, that is a real positive. Just ending up here with some contacts, and all of these resources are available online. You don't need a special library access to follow up on any of those. I'd like to acknowledge some of the other people that have fed ideas into our project and into our research. Bob Kirk, Sonia Giovanazzi, PhD student Sue Young Ko, David Holland, Craig Davis from LA, who's spent 18 years repairing the waterway system in Los Angeles after the earthquake, Marnie Brosnan for taking a lot of the images, Christopher Gomez, who's doing a comparison with Tohoku and Christchurch, Mark Quigley and Murray Hicks, scientists at the university and NIWA, have contributed. And thanks also to a lot of organisations that have helped us out with our research collectively.